Okay, this lecture is our second lecture regarding energy. Let's just do a little bit of review first. Energy, remember, energy is the ability to do work. And there's two main types of energy. We'll talk about kinetic and potential. Remember, kinetic energy is the energy of motion, which any moving object has kinetic energy, and potential energy is determined by the position of an object. Heat is the energy associated with the motion of particles. So the faster the particles move, the greater the heat or thermal energy. And just to review units of energy, we usually use joules or calories, and 1 calorie is equal to 4.184 joules. Okay, now let's talk about enthalpy. So reactions, remember we talked about how reactions can be endo or exothermic. Remember, if they're exothermic, that means they emit energy when they occur in the form of heat. If they're endothermic, that means they absorbed energy or heat when they occur. The amount of energy absorbed or emitted can be quantified by a function called enthalpy. So the enthalpy of reaction, which you'll see written as ΔH reaction, is the amount of energy emitted or absorbed when a reaction occurs at constant pressure. ΔH reaction can be positive or negative, and the sign of that, or sign of ΔH reaction, depends on the direction in which thermal energy flows when a reaction occurs. So if energy flows out of a reaction, which means if a reaction is exothermic, ΔH of the reaction is negative. So for example, the combustion of methane has a ΔH reaction of negative 802.3 kilojoules. So the combustion of methane must be an exothermic reaction. It loses energy as it occurs, or it gives off heat or energy as it occurs. If energy flows into the reaction, endothermic, then ΔH is positive. So for example, the reaction of nitrogen gas and oxygen gas to make nitrogen monoxide, the ΔH of this reaction is positive 182.6 kilojoules. So that means this is an endothermic reaction. It absorbs heat. We can use ΔH reaction in stoichiometry problems. So the amount of heat emitted or absorbed when reaction occurs depends on the amount of reactants that actually react. So let's look at the combustion of propane, C3H8. So the ΔH reaction for the combustion of propane is negative 244 kilojoules. What this means is that when 1 mole of propane gas reacts, 2,044 kilojoules of energy is released. And then when 5 moles of oxygen gas reacts, 2,044 kilojoules of energy are released. And we get that from the balanced chemical reaction. So let's look at a calculation. So a gas tank and a grill contain 1.18 times 10 to the 4th grams of propane. We want to calculate the ΔH, or calculate the heat in kilojoules associated with the complete combustion of all of the propane in the gas tank. So we use the same reaction that we saw in the previous slide, combustion of propane, and remember the ΔH of that reaction is negative 244 kilojoules. So we start with what we're given, which is 1.18 times 10 to the 4th grams of propane gas, but we want moles of propane gas. So we divide that by the molar mass of propane. And then we know that for 1 mole of propane, we have 2,044 kilojoules of energy is released. So that's our last conversion factor. And we end up getting negative 5.47 times 10 to the 5th kilojoules. So that means that when we combust 1.18 times 10 to the 4th grams of propane, 5.47 times 10 to the 5th kilojoules of energy is released. Okay, now let's talk about changes of state. So if we go between a liquid, if we have a liquid and it becomes a gas, that's called vaporization. And heat has to be absorbed for that to happen. If we go from a gas to a liquid, that's called condensation. Heat has to be released for that to happen. If we go from a liquid to solid, that's called freezing, and heat has to be released in that process too. But if we go from a solid to a liquid, melting, heat has to be absorbed. And then finally, sublimation is going from a solid to a gas, and straight to a gas, not going through the liquid phase. And heat is absorbed in this process. The opposite is deposition, so going from a gas straight to a solid, and heat is released. So in melting, heat is added to the solid and it causes the particles to move faster. At the melting point, the particles gain enough energy to overcome the attractive forces that hold them together. The particles in the solid separate and move around in random patterns, causing it to melt. So you're going from a solid to a liquid, and you have to add heat. Freezing is the opposite of melting. This occurs when the temperature of a liquid is lowered. So kinetic energy is lost, the particles slow down, and the attractive forces pull the particles closer together. A liquid changes to a solid at its freezing point. Every substance has its own freezing or melting point. And again, if you're freezing, heat has to be lost. You release heat. So the heat of fusion is the amount of heat required to melt 1 mole of a solid. So if we look at going from solid water, ice, to liquid water, that delta H is 6.02 kilojoules. That means that when I melt ice, I release 6.02. If I melt 1 mole of ice, I release 6.02 kilojoules of energy. But if I freeze water, so going from liquid water to solid, it's associated with the same amount of energy, but it has a different sign. Delta H has a different sign. So if I freeze 1 mole of water, I have to release 6.02 kilojoules of energy. That's why that's negative. So let's look at a calculation you might have to do. So if we want to calculate the amount of heat required to melt 25 grams of ice at 0 degrees Celsius. So we start with how much ice we have, which is 25 grams. We want to get to moles, so we divide it by the molar mass of water, which is 18.02 grams. And then we know the delta H of fusion is 6.02 kilojoules per mole. So we put 1 mole on the bottom, 6.02 kilojoules on the top, and we get 8.35 kilojoules of energy. So that's how much energy is required to melt 25 grams of ice. So evaporation is molecules going from the liquid to a gas state, and you have to add heat for this to happen. And evaporation happens to particles on the surface of a liquid. The boiling point is when particles within the liquid, so not on the surface, have enough energy to overcome their attractive forces and become a gas. When heat's removed, condensation occurs. So gas is converted back into a liquid state. So the amount of heat required to vaporize 1 mole of a liquid is the heat of vaporization. So if we're looking at water going to steam, the heat of vaporization is 40.7 kilojoules. So that means if I have 1 mole of water and I need 40.7 kilojoules of energy to take all of that into the gas state. And then the opposite of that is condensation. And remember, it's the same amount of energy is required for both different signs though. So if I'm going from steam to water, I release 40.7 kilojoules of energy per mole of water. So let's calculate the amount of heat required to vaporize 25 grams of water at its boiling point. So the heat of vaporization is 40.7 kilojoules per mole. So we start with 25 grams of water. We want to get to moles, so we divide by the molar mass. And then finally, we use the heat of vaporization, 40.7 kilojoules per 1 mole of water, and we get 56.5 kilojoules. So that's how much heat is required to boil or to vaporize water at its boiling point. And then, like I said before, sublimation is when particles on the surface of a solid go directly into the gas state without going through the liquid state. And so heat must be absorbed. And the opposite of that is called deposition. So when gas particles go straight to the solid phase and heat has to be released. A really good example of this, or a well-known example of this, is dry ice. Dry ice undergoes sublimation, that's solid carbon dioxide.